Hi, we're the Ram Pump Subteam.
I'm Inigo.
I'm Melissa.
I'm Cheer.
And I'm Chang.
So the purpose of our ram pump is to redirect water from a lower elevation to a higher elevation for the chemical stock tanks and our plumbing system in the plants. And the pump consists of a rod, a plate, and a spring that is all enclosed within two checked valves. And this allows for two states, the open and the closed state. During the open state, water flows down through the effluent or through the waste valve, and it is used in the plumbing system. And during the closed state, it is redirected to the chemical stock tank. So this just shows one cycle of the ram pump. And in the open state, water is flowing down through the drive pipe through the waste valve, and this creates an acceleration that increases the drag force of the water. And eventually the force of the water overcomes the spring force, which closes the plate. Once the plate is closed, pressure builds up right around the effluent valve and water flows in through the effluent valve. And this decelerates the water, which decreases the force of the water flowing through, and the spring force eventually overcomes the drag force and the plate opens again. And this repeats. And here's just a setup of our experimental setup in our lab, and it mimics the ram pump within a plant. We replaced the height difference between the head tank and the chemical stock tank with a pressurized air chamber to simulate. And also we included a sump pump to have a running source of water so that we always have a filled head tank and a source of water flowing down through the drive pipe. And our goal this semester was to find an ideal range of K constants depending on the two states, the open and the closed states. So the spring essentially should be strong enough to pop back open once the force of the water decreases, and the spring should also be weak enough that the plate can close. So the maximum K value corresponds to the spring force when it is smaller than the drag force, and the minimum K value corresponds to the spring force when it is greater than the drag force.
In order to obtain this K constant, we need to calculate first the force required to open and close the valve. We do this with this pulley system that the last semester subteam developed. It consists on a string that goes through the drive pipe and to the pulley system, and it is connected on one end to the metal plate of the ram pump, and in the other end is connected to a barrel of water that is suspended in the air. Using the balance equations, we are able to determine that the force of the water required to open or close the valve is equal to the weight of the barrel minus the weight of the rod. These two images represent how do we calculate empirically these forces. In the first image, we can see that the valve is initially closed, so we need to add water into the barrel until the valve is open. And in the second image, the valve is initially open, and we just subtract water from the container until the valve cycles. These are the average results to open the valve. We did this experiment twice, one at the beginning of the semester and the other one was more recently, just to make sure that our results were trustable, and yeah, they make sense because they are pretty close. And this is the average force required to close the valve when it's open at the beginning. So, in order to obtain the K value, we need to work with the Hooke law, but this Hooke law depends on the compression length. So we want this law to be in terms of the spring length. So that's why we developed this material property that is K prime. K prime allow us to define a length of the spring that satisfies the K constant value that we want to achieve. So what we obtain is this graph, K prime versus the length of the spring. and the slope of this line is equal to the force required to open minus the force required to close divided by the delta x. That delta x is the compression length difference between the two states when the valve is closed and when the valve is open.
In order to find the efficiency of our pump, we looked at the pressure in the waste valve and the air chamber for one cycle of the ram pump. So this graph shows the pressure traces at the waste valve in blue, and in orange is the pressure of the air chamber. At this point here, indicated by the red arrow, the sudden decrease in pressure in the waste valve is when the plate opens, and at this point here, the sudden spike in pressure in the waste valve indicates when the plate closes, and when the plate closes, the air chamber pressure also increases because when the waste valve pressure exceeds the air chamber pressure, this indicates that water is being pumped into the air chamber, and as water enters the air chamber, the air within the air chamber is compressed, which increases the overall pressure in the air chamber. And we use these pressures to calculate the volume of water pumped during each cycle. So in order to do that, we derived an equation using the ideal gas law. So this equation is derived from PV equals nRT, where P final and P initial are pressures that we measured with the pressure sensors before and after each cycle in the air chamber. N represents the initial number of moles of air in the air chamber, which we found by taking the initial volume of air, multiplying by the air density to get the mass, and then taking that mass and multiplying by the molar mass of air to get the initial number of moles. So using the pressures that we obtained experimentally, we were able to use that to calculate the change in air volume, which is equated to the change in water volume in the air chamber. So as water is being pumped into the air chamber, the air is being compressed, so the volume is decreased, and the change in water volume corresponds with the amount of water that's being pumped per cycle. And this is important because this indicates the efficiency of the ram pump, and we want to maximize the amount of water being pumped during each cycle. In order to do that, we had to compare our experimental values with theoretical values. So in order to do that, we derived this equation for the theoretical volume of water being pumped during each cycle. And this equation was derived using F equals ma and kinematic equations, where h equals the height of the drive pipe. Delta H is the height difference between the water level in the head tank and the height that we want to pump water up to. In this case, we set it to 6 meters. Vf is the terminal velocity of water in the drive pipe, which we obtained experimentally. The way that we did this is by opening the waste valve using a string attached to our pulley system, and collecting the amount of water that exited the waste valve, and also timing that time period in order to get a flow rate out of the drive pipe in liters per second. And using this flow rate, we divided that by the cross-sectional area of the drive pipe to get the terminal velocity. And after running several trials with that, we found an average terminal velocity of 2.5 meters per second. Using this, we're able to calculate the theoretical time period in which water is being pumped into the air chamber, and also the volume of water that we should be pumping, assuming the pump is 100% efficient. And we got a delta T of 0.098 seconds and a theoretical volume of 48.82 milliliters. So this is saying that the ram pump should be able to pump this amount of volume each cycle. However, comparing this with our experimental data, the section in which the waste valve pressure exceeds the air chamber pressure is when water is actually being pumped into the air chamber, and this time period was around 0.04 seconds. So you can see that the actual time was much less than the theoretical time that we expected, which indicates to us that the water in the drive pipe is stopping much faster than we had theoretically predicted. And as a result of this, the volume of water being pumped during each cycle is also much less.
As a result, as you can see before, that our theoretical value of volume of ramp pump pumping out water per cycle is actually 48.73 milliliters, whereas the experimental value that we obtained is actually only 4.195 milliliters. And this shows that there's the efficiency of the ramp pump is only at 8.6%, which is highly inefficient. And we hypothesized that the current design of ramp pump is highly inefficient because of the head loss at the effluent valve. So as you can see on the left, which is our previous design, that the ramp pump exit, which is the waste valve or effluents, the diameter is only 1/4 inch, which comparing to the drive pipe of a diameter of 1 inch is very small. And therefore we came up with this new design where we use T connectors and more check valve and a check valve at the effluent valve or waste valve, so that the effluent valve is at 1 inch diameter, which is the same as the diameter of the check valve. We use this new design in order to eliminate as much head loss as we could at the effluent valve. And in addition to that, we also in our new design we also installed brass connectors, including brass nipples and unions, to ensure that every time we assemble the ramp pump, it is a consistent range of a distance of opening and closing the valve, since that unions can help us ensure that the threading distance of every time for every assembly is the same. And therefore this new design would help us ensure that when we're doing testing of different springs with different K values, there will be a consistent range of spring constants obtained. In addition to that, throughout the semesters, we have had multiple pressure sensors failures with the current pressure sensors that we are using, which is at 30 psi upper limit and negative 30 psi lower limit. So after these failures, we hypothesized that these results because due to that there might be the actual pressure at the ramp pump is actually higher than the pressure than what the pressure sensors are putting to us. And therefore, in order to verify our hypothesis, we purchased a pressure sensor with a higher upper limit, which is at 100 psi, so that we can verify that if around the plate there are pressure spikes during the cycles around the ramp pump, as recorded at the effluent valve. In the long term, we hope that this new design with a larger ratio between the diameter of the check valve and the diameter of the drive pipe could ensure a higher efficiency of our ramp pump, and we hope to implement this new design of ramp pump in Honduras. If there's any questions or comments, please feel free to contact us at our email or even visit our GitHub repository. Thank you very much for your time.
Thank you.
Thank you.